everyone, in our last section on fluids, I'm going to cover 8.5, the equation of continuity. And first I'd like to introduce two types of flow. Laminar flow is a smooth flow, also called streamline flow, where each particle follows its own path, called a streamline, and these paths do not cross. Above a certain speed, a fluid will undergo turbulent flow. And turbulent flow is more erratic and occurs with a high amount of internal viscosity or internal friction. And the particles form small whirlpool-like circles called eddies. Okay, let's look at the math for the equation of continuity. Consider steady laminar flow of a fluid through an enclosed tube. The mass flow rate is the amount of mass that passes through a point per unit time. So this is delta M per delta T, it would be kilograms per second. Then we can plug in for that, we can put the density is the change in volume per unit time. And then we can plug in further and say that the volume is area times the change in length in that case that passes through a point per unit time. Dividing that by time, here we have length or distance over time, which is the speed. So we can also write this as density times area times the speed. And using SI units, this is kilograms per meter cubed, meters squared, and then meters per second for the units there. Now, if we consider a pipe of varying diameter, something that looks like this, where this is A1 and this is A2, since this is enclosed and no mass can escape that container, we have to have the mass flow rate at both points equal. So we have ρ1 A1 V1 equals ρ2 A2 V2. I'm trying to use a lowercase v here to show you that this is the speed and not the volume. Now, this itself here, I'll use red, is called the equation of continuity. Now, usually, and especially in this course, we're looking at fluids of constant density, such as liquids. So in that case, the density would be constant, and we can write it as A1 area times V1 speed equals A2 V2. And this is the form of the equation of continuity that we will use. Now this product, area times speed, is called the volume flow rate. And that's the amount of volume that passes through a point per unit time in the container. Okay, let's look at how this applies to some examples. Each second, 5,525 meters cubed of water flows over the 675 meter wide cliff of the Horseshoe Falls portion of Niagara Falls. The water is approximately 2 meters deep as it reaches the cliff. Part A, estimate the speed at that instant. B, as the water approaches the falls, it passes a point in the river where the channel is narrower and shallower, having a width of 345 meters and a depth of 1.5 meters. What is the speed of the water at this point in the river? Okay, so let's look at the board. In those first few words of that example, we're told that each second 5,525 meters cubed passes a point. So that itself is the volume flow rate. So I've written that here, our volume flow rate, 5,525 meters cubed per second. And I just showed you that that's equal to AV, the area times the speed. Since this looks like a rectangular shape, we can do length times width to find the area. 2 meters times 670 meters gives 1,340 meters squared. Okay. So then setting AV equal to the volume flow rate, we can solve for that speed, which will be that number, 5,525, divided by 1,340 meters squared, giving a speed of 4.12 meters per second. Now it passes through a narrower, shallower region, and so we can apply the equation of continuity here. This itself is the volume flow rate, so you could just use this number again for the product, and essentially the equation of continuity is saying that that volume flow rate has to be constant. So we have A1 V1 equals A2 V2, and solving for that speed, A1 V1 over A2. So plugging in 1,340 meters squared times 4.12 meters per second, and then this area 2 comes from multiplying the length and width for that region, which was 345 meters times 1.5 meters. So that's what this area is here. And then that gives a speed of 10.7 meters per second. All right, one more example. What area must a heating duct have if air moving 3 meters per second along it can replenish the air every 15 minutes in a room of volume 300 meters cubed? Assume that the air density remains constant. If the duct had a cross-section that was square, what would its side length have to be? Okay, so we're given enough information to determine the volume flow rate. We know that 300 meters cubed has to pass every 15 minutes. So then we need to convert that to seconds, but we can do it right in the calculation. 300 meters cubed over 15 minutes converted to seconds, so times 60 seconds per minute, gives 0.33 meters cubed per second here. All right, and then using that volume flow rate, like the last example, we can solve this time for the area of that duct. So taking our volume flow rate divided by the speed, 0.33 meters cubed per second divided by 3 meters per second, gives me 0.11 meters squared. Now, if that duct is square, then its side lengths are the same, so our area is length squared. And then we can take the root of that area to find the length. The root of 0.11 meters squared gives me 0.33 for the side length of the duct if it is square. All right, that's it for the examples on continuity. I just want to talk briefly about Bernoulli's equation and the lift force. So the overall concept of the equation of continuity is that product, area times speed, has to be constant. So that means that if the area is low, the speed has to be high. So regions where the fluid flow is condensed will move more quickly than areas where there's a wider cross-section. An example of this is that water may flow more slowly through a wide lake and then speed up as it passes through a narrow river. Another example is if you are to pour anything, even water or honey, you'll notice that it's wider at the top and then it streamlines near the bottom. And the reason is that as gravity acts and accelerates this liquid, it speeds up, and the higher speed means it has to have a lower area. Okay, so Bernoulli's principle is another fluids principle we won't look into too much in this course. It's a long equation. You can look in the lecture notes if you want to see it. But the main concept behind it is that if the speed is high of a fluid, it will have a lower pressure. So the higher the speed, the lower pressure. They're inversely proportional. And this is what causes the lift force on birds' wings and airplane wings. So a bird or an airplane will have a wing shaped like this that's tilted upwards. What this does is it causes the streamlines above the wing to condense and pass through a more narrow cross-sectional area on the top. So since they're condensed there, the area is low compared to where they're spread out below the wing. We know from the equation of continuity that this means they're moving at a high speed. So they're moving more quickly above the wing, fluid's moving more quickly above the wing than below it. And then because of Bernoulli's principle, this high speed means that there's lower pressure above the wing than below it. So the pressure on the top is less than the pressure on the bottom. So this is very similar to what we saw for the buoyant force. This pressure gradient, or difference in pressure, creates a net upward force, so P times A will be greater on the bottom than the top, creating this net force that lifts the airplane wing in a sense, and that's what is called the lift force. Okay, so that's it for the equation of continuity. Let me know if you have any questions.